Welcome to the deep dive. Today, we're going to zoom in on optical communication. It's absolutely mission critical, right, for the AI revolution and, well, just keeping regular data centers humming.
Exactly.
Yeah.
And the main thing we're looking at today, our sort of guide, is the transcript from the Lightwave Logic annual meeting of shareholders. That just happened May 15th, 2025.
Right. So our goal here is really to unpack that meeting, pull out the key stuff for you. We want to get a handle on the big challenges AI is creating for optical communication.
And how Lightwave Logic's tech fits in, how they plan to tackle these challenges.
Hmm.
What progress are they actually making in the market, and what does the future look like here?
Yeah, and prepare yourself because some of this is pretty mind-bending. People are calling this the third revolution in optical communication.
Right.
That's like up there with fiber optics itself or the internet boom.
It's a big claim, but the scale justifies it.
Totally. And just to give you a sense of scale,
Yeah.
imagine AI factories, okay? The size of football stadiums, and they're consuming power like a small city, sometimes even up to a gigawatt.
A gigawatt. That's huge.
It's staggering. Okay, so let's dive in. What's really driving all this demand?
So if you picture these AI factories,
Yeah.
they're essentially these massive clusters, right? Packed with powerful NVIDIA GPUs, graphics chips,
Yeah.
all interconnected through super fast switches, tons of
For a
memory.
dense web of connections.
Exactly. And that web needs a level of communication, speed, and efficiency we just haven't needed before.
Okay. And the industry, folks like Jensen Huang even, they seem to agree there are, what, four main roadblocks?
Yeah, four key challenges everyone's talking about.
First one, bandwidth. We're not just talking small increases here.
No, not at all. We need to leap from, say, 100 gigabits per second per connection, which is fast already, up to 200, then 400 gigabits per second, eventually.
Oh,
A terabit per second per lane.
wow. That's like going from a country lane straight to some kind of hyperloop.
Pretty much. And that's where Lightwave Logic comes in, saying, look, our materials, these electro-optic polymers we make, they might be the key. They have the potential to handle those speeds.
Okay. Potential solution for the speed bottleneck. What's challenge number two?
Connectivity. Just the sheer number of connections needed. You got tens, maybe hundreds of thousands of these GPUs all needing to talk to each other.
Right.
And the rule of thumb people use is about 6 optical transceivers. Those little things converting electricity to light and back for every single GPU.
6 per GPU. Multiply that out. That's an astronomical number of transceivers.
Exactly. So immediately you're thinking, how do we even make that many?
Yeah.
And what's the cost going to be?
Yeah, volume and cost.
And Lightwave Logic's argument is that their tech, because of its inherent properties, could allow for high-volume manufacturing, potentially at a competitive cost,
Yeah.
addressing both the how many and how much questions.
Okay, that makes sense. Then the third challenge, you mentioned power earlier, the gigawatt figure. That sounds like maybe the most urgent problem right now.
It's definitely a huge concern. These AI clusters are incredibly power hungry. We're talking potentially gigawatts for a large facility. A lot of that comes from the GPUs themselves. The latest ones like NVIDIA's Blackwell, people are estimating maybe 1,700 kilowatts per rack.
Per rack, that's just, wow.
Yeah. So any efficiency gain, anything you can do at the component level to save power, it becomes really significant when you scale it up.
So how does Lightwave Logic help with the power problem?
They see two main ways. First, their electro-optic polymers work at really low voltages, like under 1 volt. Less voltage means less power needed to drive them.
Okay, lower operating voltage. What's the second way?
The second is about signal quality. They claim their tech helps create a cleaner optical signal transmission.
Cleaner signals. Why does that matter for power?
Well, think of it like listening to someone talking. If their voice is clear, you don't have to strain to understand. If the optical signal is cleaner, the receiver at the other end doesn't have to work as hard, doesn't need as much complex, power-hungry processing to figure out the data.
Ah, I see. So less work for the receiving chip.
Exactly. It could potentially reduce or even get rid of the need for these power-intensive digital signal processors, DSPs. So you save power on both ends, making the light signal and interpreting it.
Clever. Okay, bandwidth, connectivity, power. What's the fourth challenge?
Integration. Packing everything together. When you have systems this complex, all the optical parts and the electronic parts need to be crammed incredibly close together, very tightly integrated.
Like building a Swiss watch, but for data.
Kind of, yeah. It needs to be compact, efficient, everything working seamlessly. And crucially, the optical tech needs to play nice with standard semiconductor manufacturing processes.
CMOS compatibility, right?
Exactly. CMOS compatibility, that's key. Lightwave Logic stresses that their polymers are CMOS compatible. They can be integrated using standard techniques, which makes them suitable for advanced packaging, putting optics right next to, or even on top of, the electronics.
And that tight integration helps with speed and power too, I assume?
Definitely. Shorter distances, less loss, better performance overall.
Okay, so those are the big demands. How does Lightwave Logic position their specific technology to meet them? Where do they see it fitting in?
They talk about three main application areas. First is what they call scale out. Think of this as connecting different racks of servers, maybe across a data center floor.
The longer connections within the building?
Right. This is where you need high-speed optical transceivers running at, say, 1.6, maybe 3.2 terabits per second overall. And those transceivers often use lanes running at 200 or 400 gigabits per second, the speeds we mentioned. That's a big current market for them.
Okay, scale out. What else?
Second is CPO, co-packaged optics. This is kind of the next step, getting the optics much, much closer to the main electronic chips, the GPUs, the network switches.
The closer integration.
Much closer.
Yeah.
Jensen Huang at NVIDIA talks about this a lot. It's seen as a key evolution for future systems. And Lightwave Logic's tech, being CMOS compatible, is well suited for this.
In the third area.
That's scale in. This is about connections within a single server rack, maybe even between chips on the same board. Right now, that's mostly done with copper wires.
Shorter distances.
Very short. But even there, data rates are getting so high that optics might eventually be needed. That's more of a future play, but they see potential there too.
So addressing current needs with scale out, the near future with CPO, and the longer term with scale in. Makes sense. What about the market size? How big is this pie they're aiming for?
Well, they cited estimates from Light Counting, looking out to 2028. Just the AI part, transceivers and CPO, could be around $10 billion.
$10 billion for AI optics alone.
Yeah, and that might mean something like 160 million individual modulators needed. Those are the core components using their materials.
Okay, and beyond AI.
Traditional data centers, another $7 billion or so, maybe
Oh, yeah.
70 million modulators running at 100 GBPs per lane or faster. And then there's telecom, also around $7 billion, but fewer, more complex modulators, maybe 4 million.
Those are some serious numbers. So what slice does Lightwave Logic think they can realistically get?
Based on the value of the modulators themselves, they estimate their addressable market in 2028 could be somewhere between $1 billion and $2.5 billion.
Still a very significant target.
Definitely. And they also hinted at potential future markets beyond just communications, quantum computing, aerospace, defense, maybe even consumer electronics eventually. But that's further down the road.
Right now, it's about optical communication. What do they need to do to capture that $1 to $2.5 billion? What are the critical milestones?
The absolute key is securing what they call design wins.
Mm-hmm.
Getting major companies, the ones actually building the transceivers and integrating the optics, to choose Lightwave Logic's technology for their products.
Getting designed into the final product.
Exactly. They need multiple big wins against competing technologies. And they mentioned a strategic shift too. They're focusing less on making finished devices themselves and more on their core strength, the materials, science, and licensing their intellectual property.
Focusing on the materials and the IP. Okay. Did they mention anything from the recent big industry conference, OFC, Optical Fiber Conference?
Yeah, they did. The big takeaway from OFC this year was a really strong industry push towards those faster 400 gigabit per second per lane speeds. The speed jump we talked about. Right. And that apparently generated a lot of interest, a lot of traction for Lightwave Logic, both from established silicon photonics players and some newer companies entering the space.
So the market is moving in their direction.
Seems that way.
Yeah.
They also noted significant investment happening in optics over in Asia, Singapore, Malaysia, China, Taiwan. A lot of it seems spurred by NVIDIA's partnerships with TSMC, the big chip manufacturer.
Interesting geographical shift or concentration, maybe?
And related to that, they're seeing more of the big semiconductor foundries investing in adding silicon photonics capabilities, which could mean more potential manufacturing partners for Lightwave Logic down the line.
Okay, let's talk about that design win process. It sounds crucial. You said it's 4 stages.
Yeah, they laid out 4 stages. Stage 1 is technology selection. This usually takes, say, 3 to 6 months. It starts with NDAs, non-disclosure agreements.
Standard stuff.
Right. Then they have to demonstrate their tech is superior. Better performance, crucially, stability and reliability. That's key, because polymers historically had some reliability concerns.
Addressing the old worries.
Exactly. Plus, advantages in size, power, cost, and importantly, scalability. Can they make enough of this reliably? Basically, proving their tech is ready for prime time.
Makes sense. If they pass stage 1, what's stage 2?
Stage 2 is product design, also around 3 to 6 months. Here, Lightwave Logic provides customers with process design kits, PDKs.
PDKs, what are those?
Think of them as like blueprints and pre-designed building blocks. They let chip designers integrate Lightwave Logic's polymer structures into their own chip layouts using standard design software.
So it makes it easier for the customer to use their tech.
Precisely. They also collaborate closely on the specific modulator design, help select a manufacturing foundry, and work through the reliability aspects of the combined product.
Okay, tech selected, product design. Then stage 3 must be actually building it.
Yep. Stage 3 is prototyping and qualification. This is the longest phase, typically 12 to 18 months. They build prototypes, alpha, beta, final versions, lots of testing.
Rigorous testing, I imagine.
Extremely rigorous. It has to meet the tough standards for data centers, AI factories. They're also working out the manufacturing kinks, optimizing the process for good yields during this stage.
And the final stage, stage 4.
Stage 4 is the ramp to volume production. This is when the customer's end product, using Lightwave Logic's tech, is qualified and starts shipping in volume.
And that's when Lightwave Logic starts seeing real revenue?
Yes, through material sales and potentially royalties based on the customer's sales.
Yeah.
Stage 4 also involves ongoing support and usually collaboration on the next generation of products.
So where are they now in this process? How many customers are in the pipeline?
They said they have about 20 customers in the overall pipeline, kind of trying to get into stage 1 or 2. They currently have 10 customers who are actively in stage 1 or stage 2.
Okay, 10 active engagements.
And they have one customer, Polariton, who they could name publicly, who is already in stage 3.
Stage 3, so prototyping and qualification.
Right. And their target, their goal, is to get 3 to 5 customers into stage 3 by the end of this year, 2025.
Which would position them for?
Volume production, potentially starting late 2027 or into 2028, based on that 12-18-month stage 3 timeline.
Now, you mentioned Polariton is the only one they named. Why the secrecy around the others? Investors probably want to know who these potential big customers are.
Yeah, they address that.
Yeah.
It really comes down to competitive sensitivity for their customers. Knowing exactly which advanced components, like Lightwave Logic's modulators a company is using, can give their competitors valuable intelligence about their product roadmap and capabilities.
So the customers insist on confidentiality.
Usually, yes. Polariton was a case where both sides agreed there was a mutual benefit to making it public, but that seems to be the exception rather than the rule.
Understood. Let's circle back to the core technology itself. Why optics? Why can't we just keep using faster electrical wires for AI? What's the fundamental problem?
It boils down to physics, really. Electrical signals just struggle at the speeds and distances involved inside these massive AI systems. The data rates are so high, moving between thousands of GPUs and memory banks. Copper wires start to suffer from signal loss, distortion, interference. It becomes impractical.
So light is just better for moving lots of data quickly.
Over these kinds of distances and at these speeds, yes. Light signals, traveling through fiber optics or integrated waveguides, can carry much more data, much faster, with significantly less degradation.
And silicon photonics has been the main way to do this so far, right? Using silicon?
That's right. Silicon photonics has been a huge success story. It leverages all the existing infrastructure and know-how from decades of silicon chip manufacturing. Very powerful.
There's always a but.
But yeah, it's starting to hit performance limits, especially as the industry pushes towards 400 GBPs per lane and thinks about going even faster. Silicon itself has certain physical limitations.
So we need something more.
We need materials that can augment or surpass silicon in key areas, particularly for modulating light at high speeds and low power.
And that's the niche Lightwave Logic is targeting with their polymers.
Precisely. Their polymers offer potentially much better performance, speed, and power efficiency compared to what you can achieve with silicon alone. And critically, because they're CMOS compatible, you can add them to existing silicon photonics platforms, kind of like giving silicon photonics a turbo boost where it needs it most.
You mentioned an electro-optic coefficient earlier. Can you simplify that? Why is theirs being higher a big advantage?
Okay, think of it like this. The electro-optic coefficient measures how much a material changes how it bends light when you apply electricity. A higher number means it's more sensitive. A small electrical voltage causes a big change in the light.
More bang for your buck, electrically speaking.
Exactly. So you need less voltage, less power. to switch the light on and off quickly, which is how you encode data. Lightwave logic claims their polymers are over 200 picometers per volt, whereas a traditional material like lithium niobate is around 31.
That's a pretty big difference.
It's a significant difference, yeah, potentially leading to faster modulators that use less power.
Now, reliability, that's always been the question mark over polymers in these kinds of applications. What did they say about progress there?
They were quite clear they've made major breakthroughs, especially in the last, say, 6 months to a year. It comes down to two things: the actual chemistry, the design of their light-sensitive molecules, the chromophores.
The core material science.
Right. And also developing better methods to protect the polymer once it's part of a device, encapsulating it properly. They seem much more confident about reliability now.
How does their polymer approach compare to, say, lithium niobate, which you mentioned as another high-performance material?
Lithium niobate is well established, but Lightwave logic argues their polymers have advantages. Besides potentially better performance, integration is a big one. Polymers can often be applied using spin coating, which fits relatively easily into silicon photonic manufacturing flows.
Spin coating, like spreading it onto the wafer.
Yeah, basically. Integrating lithium niobate onto silicon can be more complex, sometimes involving bonding separate chips together, which can add cost and complexity. Plus, polymers could potentially be processed on larger wafers, leveraging the scale of silicon manufacturing, which could lead to lower costs compared to lithium niobate often made on smaller, more expensive wafers.
And they're working on making their own material production wafer scale, too.
Yes, that's a key operational goal for them, moving their own polymer synthesis and preparation to wafer scale processes to drive down costs and increase volume.
What about testing? How are they proving these materials can survive in a hot, busy data center for years?
They mentioned standard, rigorous industry tests. Telcordia damp heat testing is a big one, 85 degrees Celsius, 85% humidity for extended periods. That's really tough.
Sounds brutal.
It is. It simulates harsh, accelerated aging. They also do high optical power testing, making sure the intense light itself doesn't damage the material over time. The target is typically 10-year reliability, meeting telecom standards.
And they mentioned glass transition temperature, TTG. How does that relate?
Right, TJ is the temperature where a polymer starts to soften and lose its structural integrity. A higher TG is better for stability at operating temperatures. They said their material has a TG around 180 degrees Celsius. They contrasted that with a hypothetical material with a TG closer to operating temps, say 85 degrees C, which might only last hours under stress, whereas their higher TG material is designed for that long-term 10-year target.
And all this testing and manufacturing is CMOS compatible.
That's the goal, yes. To ensure the entire process, from applying the polymer to protecting it, fits within standard semiconductor foundry practices.
They also mentioned something about the potential bandwidth being much higher than needed today, up to a terahertz.
Yeah, that was interesting. The inherent capability of the material, its physical response time, might support frequencies up to a terahertz. Current systems need maybe 120, 140 gigahertz for 400 GBPs per lane.
So there's a lot of headroom.
A lot of headroom. It suggests the material itself won't be the bottleneck for several future generations of speed increases. It's future-proofed in that sense.
Okay, let's shift to the business side. They're moving from R&D towards being a commercial operation. What are their main focus areas for that transition?
They listed several key things: bringing more rigor to all their processes, scaling up material production, making larger quantities consistently, establishing robust partner processing, working with foundries, building out their reliability testing infrastructure, ensuring they have the right high-speed design expertise in-house, and just generally putting solid business processes in place.
Sounds like a lot of operational heavy lifting.
It is. They mentioned specific investments, like working with third parties on reliability testing, buying new equipment for material scale-up, and developing next-gen materials, co-designing devices with partners like Polariton.
And developing those PDKs we talked about.
Yes, continuing to develop and refine the PDKs is crucial for customer adoption. Also focusing on the back-end processing steps, things like etching the polymer precisely and encapsulation to protect it. It's about making the whole thing manufacturable and reliable at scale.
Reviewing policies, procedures, sounds like growing up as a company.
That's a good way to put it. Optimizing the team, setting up sales channels, especially in Asia where a lot of the manufacturing happens. Investing in their own labs, too. They mentioned state-of-the-art test gear capable of handling up to 110 gigahertz.
And what's the overall business model here? How do they plan to make money?
It's primarily a materials and intellectual property licensing model. They want to sell their specialized polymers and then earn royalties based on the success of the products that use their tech.
So not primarily selling finished chips or transceivers themselves.
Not primarily, no. The idea is this model gives them potentially high gross margins. They mentioned targeting 60% plus with lower operational costs and capital expenditure compared to running their own massive chip fabs.
Leveraging partners for the manufacturing?
Exactly. They highlighted their financial position around $25 million in cash, no debt, and access to more capital through existing financing arrangements if needed. They feel their past investments, over $100 million apparently, mean they don't need huge new capex to scale this model.
Sharing the risk and reward through royalties.
That's the plan. And they emphasize their strong IP portfolio, over 70 patents, as backing this up. The message was clear. The tech is progressing. The market is there. Now it's all about execution, building a real commercial business.
Okay. The shareholder meeting also had a Q&A. Did any key points come up there that add to the picture?
A few interesting things. They said they'll provide updated financial forecasts in the coming quarters, presumably as those customer engagements move into later stages. That's something investors will watch.
Makes sense. What else?
They acknowledged awareness of the share price and its impact on retail investors, but stressed their focus is just on executing the plan, believing that will drive value. They explicitly said they're not currently focused on being bought out or seeking a takeover.
Building the business themselves is the priority.
Seems so. They also confirmed they're actively managing their IP patents and trade secrets, and that royalty discussions typically begin in stage 2 and get finalized in stage 3, considering market factors and the customer's product.
Any clarification on that target of 3 for 5 customers in stage 3 by year end?
They reiterated it's a key internal target, but whether they can announce them publicly will depend on getting customer consent, which isn't guaranteed, as we discussed.
Right, it's a confidentiality issue.
They also touched on the 400 GBPs target again, clarifying it refers to the speed per lane in the modulator. These faster lanes will enable the next generation of overall transceiver speeds, like 1.6 terabit and 3.2 terabit transceivers. That's the main market they're targeting for that 2027-2028 timeframe.
Okay, so the 400G is the building block for even faster total speeds.
Exactly. They gave a ballpark price for a current short-reach 1.6T transceiver, around $1,000, and suggested their material could potentially enable lower-cost versions.
Interesting. Any comments on competition?
They stated they see limited direct competition doing exactly what they do with high-performance electro-optic polymers. The main competition is really the established technologies, like lithium niobate or potentially enhancements to silicon photonics itself.
And how are they managing that pipeline of 20 potential customers?
They're prioritizing those they think can move quickly into stage 1 or 2. Engagement involves initial talks, NDAs, then deeper technical discussions.
What about their cash runway? Are they comfortable financially?
They express comfort that their current financial position, plus the available financing facilities, gives them the flexibility they need for the next few quarters as they push towards commercialization. They also acknowledged a need to perhaps communicate more effectively with retail investors beyond just their website updates.
Okay, good context from the Q&A. Let's try to wrap this up then. What are the main takeaways for you from this deep dive?
I think, first, just reinforcing how absolutely vital optical communication is becoming for AI. It's not just nice to have, it's fundamental. Second, the scale of the challenges, bandwidth, connectivity, power, integration is immense.
Huge hurdles.
Huge. But third, Lightwave Logic presents a compelling story about how their specific polymer technology could offer real solutions, particularly on speed and power. Fourth, they seem to be making tangible progress with customer engagement and have made significant strides on the historical reliability concerns with polymers.
And strategically positioned for a big market.
Right. They positioned themselves strategically to try and capture a slice of this massive growing market driven by AI infrastructure needs.
Yeah, I agree. Some definite aha moments, just grasping the sheer scale of this AI build-out and realizing that new materials science might be the key enabler. This really could be a third revolution, as they call it.
It really could. And hopefully this deep dive into their own shareholder meeting gives you, the listener, a solid shortcut to understanding the dynamics in this really complex, fast-moving space.
Absolutely. So maybe a final thought to leave you with. What happens when the speed of light itself starts feeling like a constraint? It sounds futuristic, but as computation gets faster and data moves quicker, maybe it's not so far-fetched. It really highlights how crucial these kinds of material science innovations, right down at the molecular level, are for unlocking whatever comes next in technology.
Definitely something to think about. Keep an eye on AI infrastructure and optical networking trends. It's going to be fascinating to watch.
Thanks for joining us on the Deep Dive.